the singularities and poles of analytic function. What do you mean by singularity, poles, zeros of analytic function? So today I start with zeros of analytic function. So what do you mean by zero? Zero means, if we talk about the zeros of any polynomial you studied previously, then what is zeros of any polynomial? Zeros of any polynomial means, if I have polynomial x plus 2, then 0 of that polynomial is the value of that polynomial becomes 0 for what value of this x. If I say this x is minus of 2, then minus 2 plus 2, it becomes 0. Hence x equal to minus 2 is the 0 of that polynomial. Clear? Similarly, in case of that analytic function also, 0 of an analytic function is a 0 of analytic function is the value of z such that fz becomes 0. Means that value of z, when we substitute that, it gives 0. Clear? So it is called the simple 0. Next, there are some order for the 0 also. If I say our f of a, if a z equal to a is 0 of any analytic function, if z equal to a is the 0 of an analytic function, then f a equal to f dash of a derivative of this equal to f double dash of a equal to, and so on up to f of m minus 1 dash a equal to 0. But f of m dash a is not equal to 0. So for all derivatives up to m minus 1 gives the value of that function equal to 0, but at m derivative the value of function cannot become 0. Hence then we can say z equal to a is called zeros of order m. Zeros of order m. So one is the simple 0, other is the zeros of order m if we have its derivative. So next, simple 0 is called 0 are isolated, means it have no neighborhood point such that function is going to be 0, going to becomes 0. So that is called simple 0, or we can say isolated 0. Next we go for singularity of an analytic function. Singularity, or we can say singularity means singular point. So singular point, we can say a point but it ceases to be analytic function is called singularity of any function. Means if we can say fz is a function, we can say hence if fz be any function, and we can say z minus 1 modulus of z minus 1 less than delta is any circle such that delta is always greater than 0. Means radius of circle is a and delta is the region, so such that enclosed no singular point other than a, means this function has if one singular point, that at this point if it is not analytic, then, and this is the circle and it encloses none of other point than A, then it is called the isolated singularity, or we can say isolated singular point. Singular point. So there are different kind of singularity. In this case, if no neighborhood is there, then we can say Z equal to A is isolated singular point. Next, we equal to Z plus 3 divide by Z minus 1 and Z of minus 2 is analytic everywhere other than at Z equal to 1, at Z equal to 2, because when we put Z equal to 1, it goes to be 1 something by 0 going to be infinite. Z is equal to 2 also gives the value. So this function at Z equal to 1 and at Z equal to 2 is not analytic. Hence, Z equal to 1 and Z equal to 2 is the singular point. Points. Hence, Z equal to 1 and Z equal to 2 are called only the singular points where the function is not analytic. Hence, there is no other singularity of neighborhood at Z equal to 1 and Z equal to 2. So, we can say these are the isolated singular points. These are called isolated singular points. Similarly, if we go for another example, fz equal to 1 upon tan of pi by z, tan of pi divided by z. Now, for what value of z? Our function is not analytic, that was the singular point. So, if I say, because if denominator equal to 0, it means for that point it is not analytic. 1 by 0 goes to infinity. So tan of pi z equal to 0. I want to find out the singularity or singular point for this given function. For this we can say for pi z equal to n of pi. For every n pi value, tan of this equal to 0. If I cancel out pi with pi, it means my z, value of z is 1 by n. So, for every value of n where n is going from 1 to infinity, n is going from 1, 2, 3 and so on. So for n equal to 1, 2, 3 up to so on is the singularities for given function. Thus z equal to 1, z equal to 1 by 2, z equal to 1 by 3, z equal to 1 by 4 and so on are the singularities where it gives the function not is analytic. Next we can say z equal to 0. These all are the isolated singularity for given function, or we can say isolated singular point. But z equal to 0 is not isolated because in the neighborhood of z equal to 0, the higher value of n, the other values of larger value of 1 by n is coming between this its circle. Hence we can say z equal to 0 is non isolated singularity. Singular point. Clear? So these are the some example of zeros, or we can say singularity. Next we go now types of singularity. There are different types of singularity. So which type of singularity? Because the singular point, different types of singular points have different name. So first is singular points. Second, we can say some singularity is called as poles. So which kind of singular point is called poles? Another is the residue. So what kind of singularity is called residue? Singularity, first type of singularity is the removal singularity. When we discuss about the types of singularity, before we see that, consider fz be a function which is analytic within the domain D, which is analytic within domain D. So this function is analytic within domain D except the value z equal to a, means only at this point it is not analytic, means z equal to a is the singular point, and this is the isolated singularity. Which kind of singularity? This is one isolated singularity because none of other singular points is finding inside this domain D. So only z equal to a exists inside domain D. So z equal to a is called isolated singular point. Hence, by the Lorentz series, if we expand this our analytic function fz by Lorentz series, then we see that Lorentz series have two parts of this function. One is the positive power of z, another is the negative power of z. So we can write like this: n going from 0 to infinity, an is the constant, z minus a to the power n is the positive part of given function, plus summation n going from 1 to infinity bn z minus a to the power minus of n. So there are two parts, one is positive power of z, second is negative power of z. Hence we can more focus on this part, because when we find out the singularity or singular point of any given function, what we can find? We can find at what value denominator goes 0. If denominator goes 0, it means that that point cannot be the analytic. At that point function is not to be analytic. So we need the denominator part. Denominator part means negative power of z. So we can say, if this is our principal part, then now we can discuss about the different types of singularity. I say first singularity is the removal singularity. So what is the removal singularity? I explain you with one example. If I have a function fz equal to sine of z minus a, divide by z minus a. Clear? So at this function we can see denominator z minus a. So z equal to a is the singular point. Clear? Because at z equal to a, this function becomes is not analytic. So z equal to a is the singular point. Now I say this is the removal singularity, because if we remove this principal part, then we can go. How we remove? We can expand the sign series 1 upon z minus a at one side. What is sign series? If I say sin x equal to x minus x cube by factorial 3 plus x 5 by factorial 5 and so on. So what is my x? Is z minus a. So what is this? This is z minus a minus z minus a whole cube. Only odd terms are there upon factorial 3 plus z minus a whole to the power 5 by factorial 5 minus alternative and so on. So we can open this sign series. After opening the sign series, we can attach this 1 minus z by z minus a to all the terms. So what becomes? First term becomes 1 minus z minus a whole square by factorial 3 plus and so on. So here we can see we remove the principal part. Now note none of term gives the negative power of z. So hence if we remove the z minus a or negative power of single z minus a from the denominator, so this function becomes analytic at z equal to a. So this type of singularity is called removal singularity. Hence fz equal to sine of z minus a upon z minus a is equal to 1. If I put z equal to a, all terms become 0, function gives the value 1. So at z equal to a. So this is called removal singularity, first type of singularity. Now we go for the next type of singularity is essential singularity, or we can say isolated singularity. So next type of singularity is essential singularity. Now again I will explain you what kind of singularity is called essential singularity with one example. If I have one function fz equal to sine of 1 by z minus a. Clear? So z minus a, where z equal to a is the singular point. Clear? So if z equal to a is the singular point, and if we expand this series sine of 1 upon z minus a, it means our function x equal to z minus a. So first term is the x, so I will write 1 minus z minus a minus 1 by factorial 3 z minus a to the power cube plus and so on. So in this we can say that the denominator never vanish, or we can say there are the infinite number of terms of negative power of z minus a. So z minus a means principal part of this fz consists infinite term. So if in essential singularities principal part part consists in finite terms, then this is called essential singularity. Means principal part have not finite terms. Next, my third type is called pole. So pole is what? Pole is exactly one kind of singular point, but which kind of singular point or which kind of singularities is called pole. So for pole, three types of singularity. This is the third. First one is the removal, where we can remove that singularity by expanding the series or in any other method. Second is, so when we remove the removable singularity, means principal part becomes zero. Principal part have no value. All negative power of z minus a terminate. Next, essential singularity. For essential singularity, principal part have infinite number of terms. So third one is the pole. Means pole is the function where principal part have some finite terms, means not zero, not infinite, but some finite term. That singular point is called pole. So if there are finite number of negative power terms of z minus a are there, so that is called the pole at z equal to a. For example, if I again explain this with example, if fz equal to sine of z minus a upon z minus a to the power 4. So in this case, we can see when we expand, then after expanding, after some term, negative power will terminate. It means same 1 upon z minus a to the power 4 is outside. Expansion of sine series is z minus a minus z minus a whole cube upon factorial 3 plus z minus a whole 5 upon factorial 5 minus and so on. When we merge this outside bracket inside, then what it becomes? 1 upon z minus a whole cube minus 1 upon factorial 3 z minus a only plus z minus a upon factorial 5 minus and so on. So in this we can see only the first two terms have negative power of z minus a. After that it will be vanished, no negative power of. So if principal part have finite number of terms, then we can say z equal to a. At that point the singular point is called pole. With pole of order, which order? So first term of this b1 is only, this is the third term, because b1 is the power of 1, b2 is power of 2, b3 is power of 3. So principal part is, this is the third term. So this is the pole of order 3. Hence for this question, z equal to a is the pole of order 3. Clear? So this is called pole of order 3. And the last is the residue of an analytic function. If z equal to a is the pole, if z equal to a is pole of a function, then is pole then the b coefficient of b1, then the function fz b1 is the called coefficient of the function, means from the Laurent series. What is the pole of, means it have finite number of the negative power of. So first term is the b1, where the coefficient of z minus 1 upon z minus a in the Laurent series is fz at z equal to a is called the residue at its coefficient is what, b1 z minus. So its coefficient is called residue at z equal to a. Clear? So these are the types of singularity. First is the removal, second is the essential, third is pole, fourth is residue. Residue is the one, if we have a pole, then the first term b1, coefficient of that b1 is called the residues at z equal to a. Now we drill on the sum. What are the singularities and all that thing? Now we can find if we have any given question like that. I have some function. Number 1, if I have fz equal to z square plus 16, then find the order of the zeros of given function. So my fz is this order of 0, means first we start with how to find the 0. For 0 of any function, what is 0 of any function? 0 of any function means the value, at that value fz becomes 0. So we can put fz is z square plus 16. So z square plus 16 equal to 0. Hence it gives z equal to plus minus 4 of iota. Clear? It means this is the 0 of given function and this have no power. It means we can say no repetition of 0 term. So it is the simple 0. Which type of 0? Simple 0. Next, another function. If I have z square minus 2 divided by z4. Now if we find out the 0 of this function, same we have to take the numerator and equate equal to 0. So when we equate z square minus 2 equal to 0, so it gives z equal to plus minus of root 2. It means if we put this value here, then numerator becomes 0. 0 divided by anything gives 0. Correct? So it is the simple 0. Which type of 0? Same. It is the plus 2 and root 2 and minus root 2 are the simple 0. Next, for 1 upon z to the power 4, because it is in denominator. So when denominator becomes infinite, it means if I say, what becomes, if I separate it, it becomes z square f of z gives z square upon z4 minus 2 upon z4. So 1 z square cut with and gives only 1 by z square. So 1 by z square, when we put z equal to infinity, then it is a 0 of order 2. Z equal to infinity is 0 of, because their power is 0, 2. So 0 of order 2. Clear? Next, if we want to discuss for some exponential function, my next function is like that. If f of z is given by e to the power z minus a upon z minus a whole square. So find the zeros or singular point, or we can say it's have pole, essential, singularity and what. So for this, if we have any exponential or trigonometrical function, first we should expand it. So when we expand, it expand like e to the power x. So what is the expansion of e to the power x? E to the power x is 1 plus x square by factorial 2 and so on. So when I expand it, 1 upon z minus a whole square is outside and it gives 1 plus x is z minus a plus x square by factorial 2. So z minus a whole square by factorial 2 plus and so on. Now what we multiply all the terms inside with 1 minus z square. So new terms become 1 upon z minus a whole square plus 1 upon z minus a plus 1, this is factorial 2, so 1 by factorial 2 and so on. So hence we see there only first two terms have only the negative power of z minus a. It means Bn have finite number of negative power. It means z equal to a is the pole, and pole of what is the first term? Pole is of order 2. So it is solution is z equal to a is pole of order. If I have another function f of z equal to 1 upon sine of z minus cos of z, we have to find at z equal to pi by 4 point, we have to find the type of singularity, which type of singularity this have at z equal to pi by 4. So for the finding the poles of given function, or we can say types of singularity, first what we can do, step 1, denominator equate equal to 0. So our denominator is sin z minus cos z, so we can put sin of z minus cos of z equal to 0. So when sin of cos minus sin of z minus cos of z equal to 0, it means sin z equal to cos z. It means tan z, if we convert it into tan z, then tan z equal to 1. So for what value tan is 1? It's always n pi, it always n pi, because at pi by 4 tan is always 1, so it always n pi plus pi by 4, where n is 0, 1, 2 and so on. So for this value of z, it becomes 1. Hence we can say z equal to pi by 4 point. If n is 0, at n equal to 0, z becomes this 0 into pi by 4. So at z equal to pi by 4 is a simple pole. What? It's a simple pole. Another function, I have f of z equal to, so we have to find out the which type of singularities are there. If I have some function have different types of singularity, cot of pi z upon z minus a whole square. Clear? So we should rewrite it. Cot means cos by sine. So it cos pi z upon sine pi z into z minus a whole square. Again, for finding the singularities or pole, we should equate denominator equal to 0. So denominator sine of pi z minus a whole square equal to 0. It means two terms. First give this equal to 0, second give this equal to 0. When we equate sine pi z equal to 0, it means for what value? For n pi sine, for every value of n pi sine is 0. So sine pi z equal to sine n pi. It means pi z equal to n of pi. Pi should cancel. It means z is the point at n. So n is positive and negative for all value. N is plus minus 0, plus minus 1, plus minus 2 and so on. Hence there is no limit, so n have limit infinite, so hence z equal to infinite is the limit point of these poles. Hence it is, or it have infinite number of term of negative power. It means it Bn have infinite number of terms, so it is isolated essential singularity, because in isolated essential singularity it have in Bn contain infinite number of terms. So isolated essential singularity. Clear? Next, for this second part, z square minus, so it's twice z minus a, z minus a. Z equal to a gives 0. It means z equal to a is a pole of order 2. Clear? So z equal to a is which type of singularity? It is a pole of order 2. It is a pole of order 2. So there are different types of problem we can drill with it. I can show you one another example in the book. See there. Find out the zeros and discuss the nature of singularity. If our function is fz, z minus 2 upon z square sine 1 by z minus 1. Clear? So we can divide fz into two parts. One is numerator, another is denominator. So numerator is new function pz, denominator is another function qz. So pz equal to z minus 2 sine 1 by z minus 1. Qz is z square. Now the zeros of fz is given by when we can numerator makes 0. So pz equate equal to 0. So when pz equate equal to 0, we see z equal to 2 is 0 point. Another is z 1 minus sine 1 minus z minus 1 by z minus 1 equal to 0. So sine value 0 at always n pi. Sine cancel. So 1 upon z minus 1 equal to n pi. So what is z? Z is 1 plus 1 by n pi. So what is the limit point when put n equal to 0? When put n equal to 0, so 1 plus infinite. So limit point of this 0 is z equal to 1. Hence z equal to 1 is the isolated essential singularity at z equal to 1. So z equal to 1 is isolated essential singularity, and z equal to 2, z equal to 2 and z equal to 1. The limit point of 1 is this, hence z equal to 1 is isolated essential singularity. Clear? And also for pole we can see qz equal to 0, denominator equal to 0. So qz equal to 0, z square equal to 0, z equal to 0, repeat twice. Hence z equal to 0 is a pole of order 2. Clear? So we can drill many types of example with, we can go step by step. First we have to, if we find 0, then we numerator equate 0. If we want to find poles, then we have to equate denominator equal to 0. That's all for today. Thank you very much.